Greetings and welcome, friends. Today we're going to be talking about similarities within right triangles. It turns out if you draw the altitude of any right triangle, oh, let me choose some purple here, purple, that you actually construct, you end up creating three triangles altogether that are similar to each other by angle-angle similarity. And as a result, then you can, like, say things about their sides with, like, ratios with respect to one another. So the reason this works, by the way, is so this angle is shared and this angle is shared for both the big triangle, and even though those aren't the same right angle, they're still congruent, and for the little triangle. So the big triangle and the little triangle are similar by angle-angle similarity. There. And then you also have this one and this angle shared with this one and this angle, and for the big triangle, right? And by angle-angle similarity, things are true. So great. I love it when things are true. Example 1. Ooh, lovely. Identify similar triangles. Okay, so let's go with the big one first. So I'm going to call that STR. All right, so triangle STR is similar to triangle. So let's see, I started at the big angle, went to the right angle, and ended on the acute angle. So for the medium-sized triangle, what order of letters do I need to pick? TUR, right? So I'm starting at this angle here, which is actually congruent to that one. Right, going to the right, then to the acute. And that is also similar to who now? Soot. Yep, that's right. So yeah, so that's not that bad. Let's take a look at example 2. Right, so then you can just use a whole bunch of triangle similarity, set up some ratios, proportions, and stuff. You know what's similar or not congruent? The size of these two example rectangle with beveled edges on them, not similar to each other. Modeling with mathematics. Ooh, a roof has a cross-section that is a right triangle. How wonderful. I have a feeling that doesn't happen often. The diagram shows the appropriate dimensions of this cross-section. Find the height of the roof. Okay. All right. So I need to set up a ratio comparing two of the triangles. The height of the roof I could use as the short leg of the medium-sized triangle, or I could use it as the long leg of the little triangle. All right. Which would you rather? Short leg of, okay, so yeah, we'll call this one. And should I compare it to the little triangle or the big triangle? Yeah, the big one, we actually know all three sides, so we might as well, yeah, compare it to the big one. Okay, so let's work with the height here first. So H, this height, which is the short leg of the purple triangle I emphasized, is to what side length? Well, I was working with this left-ish triangle. You could have done the 3.1 and have a separate ratio. Maybe we will do both. But I'm going to compare it. The only other side of the purple triangle that I highlighted was 5.5, which is hypotenuse. So I want to point out that I compared short leg to hypotenuse. So that's going to equal short leg to hypotenuse for the big triangle. So what's that going to be? Yeah, short leg to hypotenuse. Yes, thank you. If I did this the other way, I could have said h over 3.1, so that was long leg to hypotenuse for little triangle, and that should equal long leg to hypotenuse for the big triangle, so that would have been 5.5 over 6.3. Also, notice the fact that the only thing that's different between these two proportions is that, yeah, these diagonals got swapped. That's actually the saddest looking 5 I've ever seen. And then, how do I solve these with math? With the algebra of it. I'll multiply both sides by 5.5 here. I don't think I know what that is. Let's see, 3.1 divided by 6.3. Wait a minute. Guys, that's like a third. No, wait a minute. No, wait, what am I thinking? Why did I think that was a third? The 0.1, I was all like, yeah! If it was, 2.1 would have been a third. My bad. Multiply by 5.5. I got the following for the height, 2.706. What is this measured in? Meters. Mm-hmm. So that's not bad. No, that's kind of samey. All right. Let's talk about this concept of a geometric mean, which is going to feel like a completely arbitrary, like, why are we talking about this sort of thing. So the geometric mean is defined as such. Okay? Seems arbitrary. This doesn't even seem related to geometry other than the fact that it's called a geometric mean. It's different than an arithmetic mean, which is like the average of two numbers. So the geometric mean of two positive numbers a and b is the positive number x that satisfies this proportion. So a geometric mean shows up anytime you happen to have the same thing in the diagonal of your proportion. How do you get from this to this? Oh, good call. Cross multiplicado. I like it, right? So x times x is x squared. A times b is ab. How do we get from this to this? Root, both sides. And technically, when we square root, we should have had plus or minus. Because there's two square roots when you're solving algebraic equations. Right, Ryan? That's right, Mr. Waddy. However, they said the geometric mean of two positive numbers is the positive number x. So we're going to exclude that minus one there. It's just going to be the positive root of a, b. So, fortunately, example 3 starts us off. Easy sauce here. This is going to be great. All right. Find the geometric mean of 24 and 48. 2048. So let's see. Let me set up a ratio. So I'll say x to 24 is going to equal 48 over x. The key when setting this up is just knowing that the diagonals both have to have the x, and that the x is going to be the geometric mean. Okay? So, geometric mean between these two things. You also could technically have jumped right into this equation. I'm a fan of this one more because I feel like visually in the up-and-coming problems, this makes more sense to me than this one. Like, my brain isn't used to this one just yet. So I try to work with the familiar rather than that which is not. Cross multiply, I'll get x squared equals, 24 times 48. 1152. Right, after we did some cross multiplication there. And then how do I solve for x? Root, both sides, plus or minus, don't forget it, but then forget the minus sign because this is a geometric mean problem. So x is going to be, I have a feeling it's approximate, or is this going to work out perfectly? Oh, no, they didn't. They did. Well, I should have thought of that. The approximation is 33.941. They actually did this over here, which is interesting. Notice 24 and 48 both happen to have 24 go into them. So they thought of that as 24 times 24 times 2, or the square root of 24 squared times 2. And do you see where they're going here? What's the square root of 24 squared? 24 times rad 2. So that's the exact value, which can then be approximated that way. But the book also gave us the decimal approximation, which is fine. Okay, so this is kind of interesting. It turns out that there's a relationship here that follows with right triangles and geometric means. Did you believe it? You believe it, don't you? This is called the geometric mean altitude theorem. That is one mean altitude. Says the following. Let's see if I can use some colors to colorize this for us. So it says the following. In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. So I draw this. Right? Hypotenuse is divided in now to two segments. Agreed? Okay. It says then that the length of the altitude is the geometric mean of the lengths of the two segments of the hypotenuse. All right. So they say that the other way we could set this up is CD over CD. Let's see. Am I going to run out of colors here? So let's see. CD over AD is going to be the same as BD over CD. Little geometric mean sort of situation here. Right? That's what they're claiming. If you want to think about geometric mean, and the word mean, if you think about it, it's like an average. Perhaps you recall that. So if I think about this as an average, you could notice that this blue segment here is somewhere in between the shorter and the longer. Right? So it's kind of the average, but not just the average, it's the geometric average, the geometric mean between those two lengths. And maybe this is helpful to you. I don't like that one. I like setting up, right, this over that, right, should be the same as this over that. So either you're comparing short to long as short to long, right, or you could be even saying long to short would equal long to short, because there's so many different ways of setting up proportions. All right, this next one is trickier to see. Oh boy. The geometric mean leg theorem. This one takes a little while longer. All right, geometric mean leg theorem. In a right triangle, the altitude from the right angle of a hypotenuse divides it into two segments. I remember that. That sounds very similar to the thing that we just said a moment ago. Okay. Like so. It says the length of each leg of the right triangle, that is the original right triangle, so that's this one. Okay, so here's a leg of that right triangle. You guys agree? The big one, the big one. So the length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse. Oh, wait a minute. Okay. And the segment of the hypotenuse that is adjacent to the leg. Okay, so the hypotenuse, I think I mixed it up. Let's see. Did I? I done mixed it up. Let's see. The length of the leg of the right triangle. We got to ask which right triangle they're talking about here. I was going to go this way. I thought it was. I thought it was this and this. Well, let's look at the diagram. They done say that AC, yep. Yeah, I interpreted it right. AC compared to the entire length, all right, and this length. Okay, so the length of the leg in the right triangle is AC. Is the geometric mean of the lengths of the hypotenuse, AB, and the segment of the hypotenuse that is adjacent to the leg, right? Because these two connect at A. So this would not be the one that I would consider for that. Okay, so for the green ones, I would have said that AC over AB is equal to AD over AC. So the AC one is the geometric mean. And if you notice, if I done swung this down, it would land somewhere in the middle of AD and AB. So it's like the average, it's like the mean of those two things. Let's see if it made sense for this other one. So that means CB is going to be the geometric mean of the hypotenuse and its adjacent leg, which would just be this piece. And notice if I was to swing this down, it's going to land somewhere in between there. It's not the midpoint. It's the geometric mean between those two lengths. So let's see. If we'd set that up, I would have said CB over AB again is going to equal BD over CB. All right, so this is the geometric mean. They call this the leg theorem because this was a leg and this was a leg of the big right triangle. The tricky thing is noticing that we use both the hypotenuse and then one of the smaller segments on this version of it, right? So it's a little bit trickier. It's a little bit trickier to spot. Takes a little bit more practice. Oh, I hit save instead of copy. Here we go. So let's take a look at this example. Let's see if we can put these to use. All right, using a geometric mean. Find the value of each variable. Okay. Did someone set up a proportion for x? All right, so this one's related to, is this a leg or an altitude? It's an altitude, so the version that I'm going to use is the altitude one, right? And that altitude should be the geometric mean of those two segments that the altitude cut the hypotenuse into. So I'm going to say x over 6 should equal 3 over x. Medium to big equals little to medium. Or x squared equals 18. Or x equals the square root of 18. Square root of 9 times the square root of 2. 3 rad 2 is exactly it. And yeah, you estimated 4 something. Why do you estimate 4 something? Yeah, the square root of 16 is 4. And it's a little bit, 18 is a little bit bigger than 16. The next perfect square is 25. So it's actually going to be less than 4.5 because 18 is closer to 16 than it is 25. Let's see. So, yeah, I no. Square root of 18, I got 4.243. Yeah, so you were so you had a pretty good guess. Okay, so for this problem, part B, notice I don't know the altitude. I do know a leg. And it says that the leg is going to be the geometric mean of what? This setup is tricky. 2 and it's 7. No, don't. It's all right. It's all right. Yeah, the tricky here is that, yeah, it's going to be the adjacent segment to the entire hypotenuse. So I'm not using AD. I'm using the entire hypotenuse here. And so that's why I had to calculate this entire hypotenuse using segment addition postulate. So let's see. So I'll have y squared equals 14. Ooh, are we going to get some estimates on the square root of 14? All right, estimate was 3.674. Square root of 14 is 3.742. All right. Okay. So, yeah, we'll do example 5. Look at this. This guy's so cool. He's got a box. I think I tried that once and it didn't work, but if I create a new one, it might. All right, look at this cool guy. He's like, I'm going to hold this cardboard box that has like 90-degree angles on it, and look at how cool this is. I can peek this way and see the bottom of the wall, and if I was to crouch down, I could see the top of the wall, and then he measures how far from the wall he is and how high up his eye line was or whatever. So yeah, so I don't think I would have used this strategy, but I also know some more strategies to find the height of that wall that we'll use later on, maybe even like tomorrow. Even tomorrow. But nonetheless, this works. Okay, now the question is, do I know an altitude or a leg? Which is it? 8.5 is an altitude. And so that's going to be my geometric mean. W is not a geometric mean. One of the things to be careful of is just assuming that the variable will be our geometric mean. So I'll say 8.5 is to W as, so I did short to long as short is to long. So as 5 is to 8.5. So yeah, the 8.5 was the geometric mean this time. Let's cross multiply. So I'll have 5 dubs equals, anyone know what 8.5 squared is? 72.25. And then I'll divide both sides by 5. And I'll have W is equal to 14.45. All right, now, I didn't answer the question. What do they want us to do? The height of the wall. So H is going to equal 19.45 when I find the total, right? And that's feet. Yeah, that's right. All right. Well, thank you for watching, mis amigos de Internet.